For this fact-finding investigation, UL developed a comprehensive test program to address wiring systems exposed to sunlight on rooftops. Our various test samples were chosen because of their expected use on rooftops exposed to sunlight and their similarity to other raceway and cable systems that were not tested but considered to be representative of those other wiring systems for test purposes. For cables, type MC cable was chosen to represent metal-clad and metal sheath cables and conduits. For example, type MC, MI, LFMC, and so on. Sizes 12 AWG, 1/0 AWG, and 500 kc mil were chosen to represent cables of the smaller, medium, and larger sizes. Type SE and TC cable was also chosen in the 1/0 size to represent jacketed cables. For example, type SE, TC, MV, UF, and so on. For conduits and tubings, type RMC and EMT were chosen to represent circular metal raceways. For example, RMC, IMC, EMT, and so on. To represent the smaller sizes, trade size 1/2 was chosen for RMC and trade size 3/4 was chosen for EMT. For the medium and larger sizes, trade sizes 1.5 and 4 respectively were chosen. Type PVC was chosen to represent non-metallic conduits and raceways. To represent the smaller sizes, trade size 3/4 was chosen, and for the medium and larger sizes, trade sizes 1.5 and 4 respectively were chosen. For other metal wiring systems, such as metal wireways, gutters, and so on, metal raceway was chosen in the 4x4 inch and 8x8 inch sizes to represent smaller and larger wireways in general. The testing was conducted at an outdoor laboratory site located in Las Vegas, Nevada. This location was chosen for its broad range of days with higher solar radiation intensity. In accordance with Table 310.15b3c from the 2011 NEC, each wiring system was tested directly on the roof and at distances of 1/2, 3.5, and 12 inches above the roof to represent a worst-case test condition. For wiring systems tested directly on the roof and at 1/2 inch above the roof surface was asphalt painted black in color to account for additional heating from solar absorption on the roof. For wiring systems tested at distances greater than 1/2 inch above the roof surface was asphalt painted white in color to account for additional heating from the solar reflection from the roof. Each roof structure was flat, approximately 5 feet off the ground, and measured 13.5 by 10 feet, with R19 fiberglass batt insulation under the roof deck. Each test sample was 10 feet long, exposed along the horizontal length of the roof surface. A thermocouple was secured to each conductor insulation midway along the length of the sample. The thermocouples were Type T, number 24 AWG. For the Type MC cable samples, the thermocouple was secured near the conductor. For samples with more than 3 conductors, a maximum of 3 thermocouples were used. The ends of each wiring system were closed with surgical cotton to restrict airflow. The wires were not energized during the testing, since the object of the testing was to obtain a measurement of the wiring system temperature increase due to the influence of exposure to the sun. Temperatures were measured at 1-minute intervals throughout the day, and the maximum temperature of the 1-minute intervals for a 5-minute time period was recorded. This resulted in 12 recorded measurements per hour. The nearby outdoor air temperature was measured in 2 aspirated enclosures located approximately 8 feet and 13 feet above grade level in the vicinity of the roofs and test samples. Wind speed was also measured in the same vicinity using 2 anemometers. Solar irradiance was measured using a pyranometer located in the same plane as the roof surface. Measurements were recorded during the months of June, July, and August of 2011. Sufficient data was recorded to enable supportable and statistical inferences regarding expected ambient temperatures for raceway and cable systems exposed to sunlight on rooftops. The solar irradiance, or solar radiation from the sun, was measured as power density in watts per square meter. The solar radiation reaching the Earth can vary depending upon several factors, including time of day, time of year, atmospheric conditions such as clouds, haze, rain, and so on, as well as geographical location. The maximum solar radiation reaching the Earth's atmosphere can approach 1,400 watts per square meter. However, 1,000 to 1,200 watts per square meter is more typical of maximum surface irradiance on a sunny day in many parts of the United States, and can be much less during the winter and much less on cloudy days. PV modules are tested and rated under what is referred to as standard test conditions, or STC for short. These standard test conditions are solar irradiance of 1,000 watts per square meter and air temperature of 77 degrees F. In the NEC, PV system components such as wire size and overcurrent protection are based on these standard test conditions, with adjustment factors for periods of time where the maximum solar irradiance exceeds 1,000 watts per square meter. Here is a graph of the solar irradiance at the test site on June 22, 2011. The day was near the summer solstice, had full sun, and maximum outdoor temperature of 110 degrees F. The solar irradiance exceeded 1,000 watts per square meter for a 3-hour period beginning at 11:10 a.m. Article 100 of the NEC defines a continuous load as a load where the maximum current is expected to continue for 3 hours or more.